Hello there, and welcome. Tonight, we're going to talk about black holes, one of the most mysterious, beautiful and strange things in the entire universe, and we're going to do it slowly, gently, like watching stars appear one by one as the sky grows dark. Black holes are places where the rules seem to break down, where time bends and light cannot escape, where gravity becomes so strong that space itself folds inward. They sound frightening at first. But there's something deeply peaceful about them too. They remind us how small we are, how vast everything else is, and sometimes that's exactly what we need to hear. You don't need to remember every detail I share tonight. You don't need to take notes or stay awake until the end. This is not that kind of journey. If your eyes grow heavy, let them close. If your thoughts begin to wander, let them drift. If you fall asleep halfway through, that's perfect. That's exactly what this is for. And if you wake up later and want to hear more, I'll still be here, speaking softly about the cosmos. The universe is so much bigger than our daily worries, and black holes are some of the biggest mysteries it has to offer. So let your mind expand tonight. Let it stretch beyond the walls of your room, beyond the sky above your town, beyond even the stars you can see. Out there, in the deepest parts of space, black holes are waiting, not to frighten us, but to show us how beautiful the unknown can be. Are you ready? Then let's begin our journey. 100 quiet truths about black holes, and we have all the time in the world. Fact 1. A black hole is a place in space where gravity pulls so strongly that nothing can escape from it. Not rocks, not planets, not even light itself. Imagine a drain in a bathtub, but instead of water spiraling down, it's everything. Space, time, matter, energy. All of it pulled toward a center that we cannot see. This happens because a massive amount of matter has been squeezed into an incredibly tiny space. The gravity becomes so intense that it creates a point of no return. Scientists call this boundary the event horizon, and once something crosses it, there's no coming back. To understand just how extreme this is, consider that on Earth, you need to travel about 11 kilometers per second to escape into space. That's called escape velocity. But at the event horizon of a black hole, the escape velocity equals the speed of light, which is 299,192 kilometers per second. Since nothing in the universe can travel faster than light, nothing can escape. The black hole becomes a prison from which there is no release, a cosmic trap where the laws of physics reach their most extreme expression. Fact 2. Black holes form when very large stars reach the end of their lives. Throughout a star's existence, it burns fuel in its core, creating heat and pressure that push outward. This outward push balances the inward pull of gravity. For millions or even billions of years, this balance holds steady. The star shines brightly, fusing hydrogen into helium, then helium into heavier elements like carbon, oxygen, and eventually iron. But when the fuel runs out, the balance breaks. Gravity wins. The star collapses inward on itself in a violent explosion called a supernova. This explosion is so bright it can briefly outshine an entire galaxy, containing hundreds of billions of stars. But the explosion is not the end of the story. If the remaining core is heavy enough, usually more than 3 times the mass of our Sun, it keeps collapsing. It doesn't stop. There's nothing left to push back against gravity. It crushes down smaller and smaller, denser and denser, until it becomes a black hole. The star that once lit up the sky, that perhaps warmed planets and created the conditions for life, becomes a shadow in space. It's a transformation so complete that almost nothing of the original star remains visible. Only gravity persists, stronger than ever before. Fact 3. The term black hole wasn't always used to describe these objects. For many years, scientists called them frozen stars, or collapsed objects, or sometimes just singularities. The phrase black hole was popularized by physicist John Wheeler in 1967 during a lecture in New York. Before that, the idea seemed almost too strange to name properly. These objects had been predicted by Einstein's equations decades earlier, but even Einstein himself doubted they could really exist in nature. He thought the universe would find some way to prevent such extreme conditions, but the math kept insisting they were possible, and eventually observations confirmed it. When Wheeler used the term black hole, it stuck immediately because it captured something essential about these objects. They are holes in the fabric of space, and they are black because no light escapes them. The name is simple, direct, almost poetic in its clarity. Sometimes the best names are the ones that tell you exactly what something is, even if you don't fully understand it yet. And there's something fitting about using everyday language to describe something so extraordinary. It makes the cosmos feel just a little bit closer, a little bit more knowable. Fact 4. Black holes are not actually holes in the way we normally think of them. They are not empty voids or tunnels to somewhere else. They are not gateways to other dimensions or passages through space and time, at least not in any way we understand. They are objects, real, physical things with mass and gravity and presence. It's just that they're so dense that their gravity warps space around them in extreme ways. Think of space as a stretched rubber sheet, smooth and flat when nothing is on it. When you place a heavy ball on it, the sheet dips down, creating a well. Other objects rolling nearby will curve toward that well. A black hole is like placing something so heavy on that sheet that it creates a pit so steep, so deep, that nothing can climb back out once it rolls in. The space around a black hole is curved so sharply that all paths lead inward. It's not a hole you fall through, it's a place you fall into, and then you become part of it. Your mass adds to the black hole's mass. Your atoms, your history, everything you were, becomes woven into this object that sits at the center of warped space. In a way, black holes are the most concentrated matter in the universe. They are stars compressed beyond recognition, collapsed into a form so extreme that our ordinary concepts of size and shape no longer apply. Fact 5. Light travels faster than anything else in the universe. It moves at about 792 kilometers per second, a speed so great that it could circle the Earth more than 7 times in just 1 second. Nothing we know of can go faster. This speed limit is built into the fabric of the universe itself, a fundamental constant that shapes how reality works. And yet, black holes trap even light. This is what makes them invisible, what gives them their name. When we look at the night sky, we see stars because their light reaches our eyes. Photons stream out from those distant suns, travel across the vast emptiness of space, and land on our retinas. But black holes emit no light. They absorb it completely. Every photon that crosses the event horizon is caught forever, pulled down into the center where we cannot follow. So when you try to look at a black hole directly, you see nothing, just darkness, a void where a star once lived. We can only detect black holes by watching how they affect the things around them, the way they pull on nearby stars, causing them to orbit around empty space, the way gas and dust swirl around them in bright spirals before vanishing forever, the way they bend the light from objects behind them. Black holes are invisible, but their presence is unmistakable. They leave fingerprints on the universe, shadows that we can trace even if we cannot see the thing itself. Fact 6. The boundary around a black hole, the point of no return, is called the event horizon. It's not a physical surface you could touch. There's no wall there, no barrier you could see or feel. It's simply the distance from the center where the escape velocity equals the speed of light. Inside the event horizon, you would need to travel faster than light to get out. But since nothing can travel faster than light, nothing gets out. The event horizon is a one-way door. You can pass through it going in, but you can never pass through it going out. It's a border between the universe we know and a place beyond knowing. What makes the event horizon especially strange is that it's not the same for everyone. If you were falling toward a black hole, you would cross the event horizon at a specific moment from your point of view. But to someone watching you from far away, you would never quite seem to reach it. As you got closer, you would appear to slow down, moving more and more sluggishly, until you seem to freeze at the edge. Time itself dilates near the event horizon, stretching and warping under gravity's influence. So the event horizon is both a place you can cross and a place you can never quite reach, depending on your perspective. It's a boundary that separates not just regions of space, but experiences of time itself. Fact 7. At the very center of a black hole, all the mass is crushed into a point called the singularity. This point is infinitely small and infinitely dense, at least according to our current mathematics. Imagine taking something as massive as a star and compressing it down not just to the size of a planet or a city or a grain of sand, but to a point with no size at all, zero volume, infinite density. Our minds struggle with this concept because we have no everyday experience that comes close to it. Our current understanding of physics breaks down here. The equations that describe gravity, the ones Einstein gave us, produce infinities when you try to calculate what happens at the singularity. Infinities in math usually mean we're missing something. They suggest that our theories are incomplete. Perhaps quantum mechanics will one day explain what really happens at the core of a black hole. Maybe there's a tiny but finite structure there, something that prevents true infinite density. Or maybe the singularity is real, and we need to expand our understanding of what reality can be. For now, it remains a mystery wrapped in darkness, a place where the rules we know simply stop working. It's humbling in a way. Despite all our science and technology, there are still places in the universe that lie beyond our comprehension. Fact 8. There are different sizes of black holes, and each type has its own story. The smallest ones, called stellar black holes, form from individual stars and typically have masses between 3 and several dozen times that of our Sun. These are the black holes created when massive stars explode and collapse. Then there are intermediate black holes, which are rarer and harder to find. They have masses between 100 and 100,000 suns. Scientists are still debating how these form. They might be the result of multiple stellar black holes merging together over time, or they might form in dense star clusters where many stars collide and combine. And finally, there are supermassive black holes, which live at the centers of galaxies and can have masses equal to millions or even billions of suns. Our own Milky Way galaxy has a supermassive black hole at its heart called Sagittarius A star. It weighs about 4 million times as much as the Sun, yet it sits relatively quiet at the center of our galaxy, not consuming much material right now. Scientists don't fully understand how supermassive black holes grow so large. Did they start as stellar black holes and gradually feed on gas and stars for billions of years? Or did they form directly in the early universe through some other process? Despite their differences in size, all black holes share the same basic properties. They all have an event horizon. They all have a singularity at their center. They all pull with gravity that nothing can resist. Big or small, they are fundamentally the same kind of object, just scaled up or down. Fact 9. Time behaves strangely near a black hole, in ways that challenge our everyday understanding. According to Einstein's theory of relativity, gravity affects the flow of time. The stronger the gravity, the slower time moves. This isn't just theoretical. We measure it with satellites orbiting Earth. The satellites experience slightly less gravity than we do on the surface, so their clocks tick slightly faster. The difference is tiny, but it's real, and must be corrected for GPS systems to work properly. Near a black hole, this effect becomes extreme. If you could watch someone fall toward a black hole from a safe distance far away, you would see them slow down as they approached the event horizon. Their movements would become sluggish. Their clock would tick more and more slowly compared to yours. Light from them would stretch to longer, redder wavelengths. As they reached the event horizon, they would appear to freeze, suspended forever at the edge, fading from view as their light became dimmer and dimmer. But from their perspective, nothing strange would happen. They would cross the horizon in finite time, perhaps not even noticing the moment they passed it. To them, time flows normally. It's only the comparison between their time and yours that reveals the difference. This means that the event horizon is not just a boundary in space, but a boundary between different flows of time. Cross it, and you step into a region where time itself operates under different rules. Fact 10. If you fell into a black hole, you would experience something called spaghettification, a term that sounds almost comical but describes something quite dramatic. This happens because gravity's pull is stronger on the parts of your body closer to the black hole than on the parts farther away. Gravity decreases with distance, so your feet, if they're leading the way, would feel much more force than your head. This difference in gravitational force would stretch you out like a piece of spaghetti, pulling you longer and thinner. For smaller black holes, this stretching would happen before you even reach the event horizon. The tidal forces, as they're called, would be so strong that they would tear you apart, ripping your body into atoms and eventually even breaking apart the atoms themselves. But for supermassive black holes, the event horizon is so far from the center that you might cross it without feeling anything unusual at first. The tidal forces near the horizon would be relatively gentle. You could pass through intact, not realizing you had crossed the point of no return. The stretching would come later, deeper inside as you fell toward the singularity. But by then there would be no escape, no way to send a message back, no way to reverse course. Spaghettification is a reminder that black holes don't just trap you, they reshape you, pulling you into a new form as you fall. Fact 11. Black holes are not cosmic vacuum cleaners. They don't roam around space sucking up everything in sight. This is a common misunderstanding, perhaps because black holes have such a dramatic reputation. In reality, their gravity only affects objects that come close enough. If our Sun was suddenly replaced by a black hole of the same mass, Earth would not be pulled in. We would continue orbiting exactly as we do now, following the same path at the same distance. The black hole's gravity at our distance would be identical to the Sun's gravity, because the mass would be the same. Of course, we would freeze without the Sun's light and heat. Plants would die, the oceans would turn to ice, and life as we know it would end. But we wouldn't spiral into the black hole. Gravity depends on mass and distance, not on whether the object is a star or a black hole. Black holes are only dangerous if you get too close, inside a certain radius where their gravity becomes overwhelming. Beyond that distance, they behave just like any other massive object. They sit in space, pulling on things around them, following the same laws of motion that govern planets and stars. Fact 12. Scientists have never seen a black hole directly with their eyes, but they have captured images of the glowing material around them. In 2019, the Event Horizon Telescope project released the first image of a black hole's shadow, a moment that marked a historic achievement in astronomy. It showed a bright ring of light surrounding a dark circle. The dark circle was the black hole's event horizon, blocking the light behind it and creating a shadow against the glowing background. The bright ring was superheated gas and dust spiraling around the black hole at incredible speeds, glowing as it was torn apart by gravity and friction. This black hole sits at the center of a galaxy called Messier 87, about 55 million light-years away. To create this image, scientists linked radio telescopes from around the world, turning the entire Earth into one giant telescope. They collected data for days, then spent years processing it to produce a single picture. Seeing that image was like glimpsing the unseeable. It confirmed what mathematics had predicted for decades. The size of the shadow matched Einstein's equations. The brightness of the ring told us about the black hole's feeding habits. This one image answered old questions and raised new ones, giving us our first real look at the edge of a black hole. Fact 13. Black holes can spin, and their rotation affects everything around them. When a massive star collapses, it often has some rotational motion, just like the Earth spins as it orbits the Sun. As the star shrinks, it spins faster, much like a figure skater pulling in their arms during a spin. This is due to conservation of angular momentum, a fundamental principle in physics. The black hole that forms inherits this rotation, and it can spin incredibly fast, sometimes at nearly the speed of light. A spinning black hole drags space and time around with it in a process called frame dragging. It creates a region called the ergosphere just outside the event horizon. Inside the ergosphere, space itself is pulled along with the black hole's rotation. Nothing can stand still there, not even light. Even if you fired your rockets at full power, you would still be swept around the black hole like a leaf in a whirlpool. This spinning creates complex effects that scientists are still studying. Energy can actually be extracted from a spinning black hole through a process proposed by physicist Roger Penrose. If you dropped something into the ergosphere at just the right angle, it could split apart, with one piece falling in and the other piece flying out with more energy than it started with. The black hole would slow down slightly, giving up some of its rotational energy. A rotating black hole is not just a pit in space. It's a whirlpool in the fabric of reality itself, dragging everything nearby into its cosmic dance. Fact 14. Black holes can collide with each other, and when they do, the results are spectacular. When two black holes orbit each other closely, they emit gravitational waves, which are ripples in space-time itself. Imagine dropping two stones into a still pond. The ripples spread out from each stone, and where the ripples meet, they create interference patterns. Gravitational waves are similar, except they ripple through the fabric of space and time rather than water. These waves carry energy away from the system, causing the black holes to spiral closer together. The orbit gets tighter and faster, and the gravitational waves get stronger and more frequent. Eventually, after perhaps millions of years of spiraling, the black holes merge into a single, larger black hole. This merger releases a tremendous amount of energy in the form of gravitational waves, more energy than all the stars in the observable universe emit as light in that same instant. In 2015, scientists detected these waves for the first time using instruments called LIGO detectors. The signal came from two black holes that had collided over 1 billion light-years away. The detected signal lasted only a fraction of a second, but it encoded information about the black holes' masses, their spins, and the distance to the merger. Hearing that signal was like listening to the universe ring like a bell. It was the first direct detection of gravitational waves and the first direct evidence that black holes truly exist and can merge together. Fact 15. Gravitational waves travel at the speed of light, and they pass through almost everything without stopping. When they reached Earth from that distant collision, they stretched and squeezed space itself by an incredibly tiny amount. The change was smaller than the width of a proton, which is already 1 million times smaller than a grain of sand. Yet our instruments were sensitive enough to detect it. The LIGO detectors use laser beams travelling down tunnels 4 kilometers long. When a gravitational wave passes through, it briefly changes the length of these tunnels by an amount smaller than an atom's nucleus. Detecting such a tiny change requires extraordinary precision and careful isolation from vibrations caused by passing trucks, earthquakes, ocean waves, and even the motion of atoms in the mirrors themselves. This discovery opened a new way of observing the universe. Before, we could only see light and other electromagnetic radiation. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. But all of these are variations of the same phenomenon, electromagnetic waves. Now we can also feel the vibrations of space-time itself. Black holes, which emit no light, suddenly became detectable through the ripples they create when they dance together in the dark. It's like humans have been watching the universe with our eyes for centuries, and now we've suddenly learned to hear it as well. Fact 16. The nearest known black hole to Earth is about 1,500 light-years away, a distance that sounds close in cosmic terms, but is still unimaginably vast. A light-year is the distance light travels in 1 year, which equals about 9.5 trillion kilometers. So 1,500 light-years is roughly 14 quadrillion kilometers. Light from that black hole, if it emitted any, would take 500 years to reach us. Even travelling at the speed of our fastest spacecraft, something like the Voyager probes that are now leaving the solar system, it would take tens of thousands of years to get there. So while black holes exist in our galaxy, they are not a threat to us. Space is so enormous that even dangerous objects remain safely distant. We can study them, marvel at them, and imagine what they're like without ever having to worry about falling into one. Our sun will never become a black hole. It doesn't have enough mass. When it dies in about 5 billion years, it will swell into a red giant, perhaps swallowing Earth, then shed its outer layers and leave behind a white dwarf, a dense ember about the size of Earth that will slowly cool over trillions of years. Black holes require stars much more massive than the Sun, and those stars are relatively rare. So we're safe, living on our small planet orbiting an ordinary star in a quiet corner of the galaxy. Fact 17. Supermassive black holes are found at the centres of most large galaxies, a discovery that has reshaped our understanding of how galaxies form and grow. Our Milky Way has one called Sagittarius A star, which has a mass about 4 million times that of the Sun. Despite this enormous mass, it's relatively quiet right now. It doesn't consume much material. It sits at the galactic centre, influencing the orbits of nearby stars but not actively feeding. Some supermassive black holes, however, are actively feeding on gas, dust, and even entire stars. When this happens, the material doesn't fall straight in. It swirls around the black hole in a structure called an accretion disk, flattened by rotation and conservation of angular momentum. Friction in the disk heats the material to millions of degrees, causing it to glow brightly in X-rays and other wavelengths. These actively feeding black holes can outshine entire galaxies containing hundreds of billions of stars. The light comes from a region smaller than our solar system, yet it blazes across the universe with incredible intensity. They are called quasars when they are extremely bright. or active galactic nuclei in general. They are some of the most energetic and luminous objects in the universe, beacons that can be seen across billions of light-years of space. Fact 18. Quasars are so bright that we can see them from billions of light-years away across almost the entire observable universe. They are powered by supermassive black holes consuming vast amounts of matter, sometimes equivalent to hundreds of stars per year. The light comes not from the black hole itself, but from the superheated material just outside the event horizon. As gas spirals inward, it rubs against other gas, generating friction and heat. The temperatures can reach tens of millions of degrees, hot enough to emit intense radiation across the electromagnetic spectrum. Quasars were more common in the early universe when galaxies had more gas available for their central black holes to consume. Looking at distant quasars is like looking back in time, seeing the universe when it was younger and more violent. Light takes time to travel, so when we see a quasar 10 billion light-years away, we're seeing it as it was 10 billion years ago. The universe is only about 13.8 billion years old, so these distant quasars show us what galaxies looked like when the cosmos was still young. They help us understand how galaxies and black holes grew together over time. Many of those distant quasars have probably quieted down by now, their central black holes having consumed most of the available gas nearby. But we won't see that change for billions of years, not until the light from their present state finally reaches us. Fact 19. Black holes can launch jets of material into space, structures so large and energetic that they dwarf the galaxies containing them. These jets shoot out from the regions near the black hole's poles at nearly the speed of light. They can extend for thousands of light-years, far beyond the galaxy itself, punching through intergalactic space like cosmic searchlights. The exact mechanism that creates these jets is still not fully understood, but it involves the black hole's spin and powerful magnetic fields in the surrounding material. The jets carry energy and matter away from the black hole, even though the black hole itself traps everything that crosses the event horizon. It seems contradictory at first, but the jets form just outside the event horizon, in the accretion disk and the regions around it, where escape is still possible. Material in the disk is caught in powerful magnetic fields that spiral around the black hole. Some of this material gets channeled along the magnetic field lines toward the poles, accelerated to tremendous speeds, and ejected outward in narrow beams. They are a spectacular reminder that black holes are not just consumers, they also give back to the universe in dramatic ways. These jets can trigger star formation in nearby gas clouds, influence the evolution of galaxies, and distribute heavy elements throughout space. Black holes shape their cosmic neighborhoods, not just through gravity, but through these enormous outflows of energy and matter. Fact 20. Stephen Hawking proposed that black holes are not entirely black, a discovery that changed how we think about these objects. In 1974, he suggested that they emit a faint form of radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, arises from the strange behavior of particles at the quantum level. Normally empty space is not truly empty. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence and then annihilate each other almost instantly. This happens everywhere, all the time, but the particles exist for such a brief moment that they usually don't affect anything. But near the event horizon of a black hole, something different can happen. One particle from the pair might fall into the black hole while the other escapes into space. To an outside observer, it looks like the black hole is emitting radiation. The escaping particle carries energy, and that energy has to come from somewhere. It comes from the black hole itself, very slightly reducing the black hole's mass. This process is incredibly slow for large black holes, producing only a faint glow far weaker than the cosmic background radiation. But over unimaginable stretches of time, it could cause a black hole to evaporate completely. This was revolutionary because it suggested that black holes are not eternal. Given enough time, they will disappear, returning their mass to the universe as radiation. Fact 21. If Hawking radiation is real, and most physicists believe it is even though we've never detected it, then black holes have a temperature. This might seem strange because we usually think of hot things glowing brightly, and black holes are by definition dark. But temperature in physics is about the average energy of particles, and Hawking radiation gives black holes a characteristic temperature. Strangely, smaller black holes are hotter than larger ones. A black hole with the mass of the Sun would have a temperature far colder than the cosmic background radiation that fills space, which is about 3 degrees above absolute zero. So stellar black holes actually absorb more energy from the universe than they emit. They grow slightly over time by absorbing background radiation, but a tiny black hole, if one could exist, would glow brightly and evaporate quickly. The evaporation speeds up as the black hole shrinks because temperature increases as mass decreases. In the final moments of a black hole's life, it would release a burst of energy, perhaps even exploding. However, this process takes so long for the black holes we observe that none of them will evaporate for trillions upon trillions of years, far longer than the current age of the universe. The universe is still far too young to have witnessed the death of a black hole. All the black holes that exist today will remain for an incomprehensibly long time into the future. Fact 22. Black holes challenge our understanding of information, leading to one of the deepest puzzles in modern physics. In quantum mechanics and classical physics, information about a system's past is never truly lost. You can, in principle, reconstruct what happened by examining the present state carefully enough. If you watch a video of a glass shattering, you could run it backward and see the glass reassemble. The information about the intact glass is preserved in the pattern of shards, but if something falls into a black hole, and the black hole eventually evaporates via Hawking radiation, where does the information about that object go? The radiation appears to be random, carrying no information about what fell in. This puzzle is called the black hole information paradox. Some scientists think the information is somehow encoded in the radiation in ways we don't yet understand. Others believe it might be stored on the event horizon itself, written into the structure of space-time at the boundary. Still others propose more exotic solutions, like the idea that information might tunnel through to another universe, or be preserved in some higher dimensional space. Resolving this paradox might require a new theory that unites quantum mechanics and gravity, something we don't yet have. It's a problem that touches on the deepest questions about reality. What is information? How is it stored? Can it ever truly disappear? Black holes sit at the intersection of these questions, forcing us to confront the limits of our knowledge. Fact 23. The event horizon of a black hole has an area, and that area is related to the black hole's entropy in a surprising way. Entropy is a measure of disorder, or the number of possible states a system can be in. The more entropy something has, the less we know about its precise internal state. A messy room has high entropy because there are many ways to arrange the objects messily. A clean room has low entropy because there are fewer arrangements that count as clean. For most objects, entropy is proportional to volume. The bigger something is, the more possible internal states it has. But for a black hole, the entropy is proportional to the area of the event horizon, not the volume inside. This surprising result suggests that all the information about what has fallen into a black hole might be encoded on its two-dimensional surface, like a hologram storing a three-dimensional image. This idea is the foundation of the holographic principle, which proposes that our three-dimensional universe might be a projection from information stored on a two-dimensional boundary far away. It's a radical idea that challenges our intuitive understanding of space. Black holes hint at deep connections between gravity, information, and the nature of reality itself. They suggest that the universe might work very differently than it appears, that the space around us might emerge from information encoded elsewhere. Fact 24. Black holes distort the appearance of objects behind them through a process called gravitational lensing, creating strange and beautiful visual effects. Because they curve space so strongly, light from distant stars and galaxies bends as it passes near a black hole. This bending can create multiple images of the same object, or stretch and magnify the background light into arcs and rings. The famous image of the black hole in Messier 87 shows a bright ring partly because of this lensing effect. The light from the backside of the accretion disk is bent over the top of the black hole by gravity, allowing us to see it even though it's behind the black hole from our perspective. It's as if the black hole acts as a cosmic magnifying glass, warping our view of everything beyond it. Gravitational lensing happens with any massive object, not just black holes. Galaxies and galaxy clusters lens the light from objects behind them, helping astronomers study extremely distant parts of the universe. But black holes create the most extreme lensing because they curve space so sharply. If you could somehow orbit close to a black hole and look around, you would see the entire sky distorted. Stars would appear in strange places. You might even see multiple images of the same star in different directions. The black hole would dominate the view, a dark circle surrounded by a bright ring of lensed light from everything behind it. Fact 25. There may be black holes that formed in the very early universe, shortly after the Big Bang, through processes completely different from stellar collapse. These are called primordial black holes, and they would be unlike anything created by dying stars. In the chaotic conditions of the early universe, regions of space with slightly higher density might have collapsed directly into black holes without ever forming stars first. These primordial black holes could have any mass, from tiny to enormous. Some might be as small as a single atom but weigh as much as a mountain. Others might be millions of times more massive than the Sun. Some scientists have even proposed that tiny primordial black holes could make up some or all of the mysterious dark matter that holds galaxies together. Dark matter is something we detect through its gravitational effects, but we've never seen it directly or figured out what it's made of. If it's primordial black holes, that would solve one mystery, though it would raise many new questions. We haven't detected primordial black holes yet, but the search continues using various methods. If they exist, they would be fossils from the universe's first moments, windows into a time we can barely imagine, when the cosmos was hot, dense, and filled with energy. They would tell us about conditions in the first fraction of a second after the Big Bang, helping us understand how the universe evolved from simplicity to the rich complexity we see today. Fact 26. When black holes merge together, they create ripples in space that travel outward like waves on a pond. These gravitational waves move at light speed and carry information about the collision across the universe. Scientists can listen to these waves using special detectors on Earth called LIGO and Virgo. Each collision sounds different, creating unique patterns like musical notes. Small black holes create high-pitched chirps that rise in frequency. Large ones make deep rumbles that shake space-time slowly. By studying these sounds, we learn about black holes that are too far away to see with telescopes. The waves pass right through our planet, gently stretching and squeezing everything by amounts too tiny to feel. They pass through mountains, oceans, and our bodies without us noticing. Every time two black holes crash together somewhere in the universe, space itself rings like a bell. If we're listening carefully with our detectors, we can hear it. These detections have opened a completely new way of observing the cosmos. We're no longer limited to collecting light. We can now feel the vibrations of space-time itself. Fact 27. Material falling toward a black hole doesn't drop straight in like water down a drain. Instead, it forms a spinning disk called an accretion disk. This happens because the material has sideways motion, not just inward motion. Everything in space is moving, orbiting, spinning. As pieces of gas and dust orbit the black hole, they rub against each other, creating friction. This friction generates enormous heat, sometimes hotter than the surface of the sun. The inner parts of the disk can reach temperatures of millions of degrees. The material glows brightly, often in X-rays that special telescopes can detect from Earth. The disk can be thousands or even millions of kilometers wide, depending on the black hole's size and how much material is available. Near the inner edge, where material moves fastest, the disk shines brightest. This glowing ring is often the only way we can spot black holes, since the black holes themselves emit no light. The accretion disk announces the black hole's presence like a bright sign pointing to an invisible object. Fact 28. Black holes can exist in binary systems, paired with normal stars in cosmic partnerships. The black hole and star orbit around their common center of mass, locked in a gravitational dance that can last millions of years. Sometimes the black hole pulls gas away from its companion star, stealing material from its outer layers. This stolen gas spirals into an accretion disk and heats up tremendously, creating bright X-ray emissions that astronomers can detect. These systems are called X-ray binaries because they shine brightly in X-ray wavelengths. Astronomers have discovered many such systems by looking for stars that seem to orbit invisible partners. The star wobbles back and forth, pulled by something we cannot see. By measuring the wobble and calculating the orbital mechanics, scientists can determine the unseen partner's mass. If it's heavy enough and emits no light of its own, it must be a black hole. These binary systems give us some of the best evidence that black holes truly exist. They also let us study how black holes interact with normal matter in real time. Fact 29. The singularity at a black hole center might not be a point at all, despite what simplified explanations suggest. Some theories suggest it could be a ring if the black hole spins fast enough. This ring-shaped singularity would rotate with the black hole, creating even stranger effects than a point singularity would. The mathematics describing spinning black holes, worked out by physicist Roy Kerr in 1963, allows for this possibility. Near a ring singularity, the warping of space and time becomes so extreme that equations predict closed, time-like curves paths through space-time that loop back on themselves. This sounds like time travel, potentially allowing you to move backward to your own past. However, most physicists think quantum effects would prevent such paradoxes from actually occurring. Nature probably has safeguards against time travel that would violate causality. The true nature of the singularity remains hidden behind the event horizon, where we cannot observe it directly. We can only guess based on mathematics and theory. Until we develop a complete theory of quantum gravity, the singularity will remain one of the deepest mysteries in physics. Fact 30. Some black holes have companion objects so close that they complete an orbit in just hours rather than years. These tight binaries are natural laboratories for studying extreme physics. The companion might be another black hole, a neutron star, or even a white dwarf. As they spiral closer together over millions of years, losing energy to gravitational waves, they move faster and faster. Eventually they will merge, combining into a single object. The final moments before merger happen incredibly quickly, in a matter of seconds or minutes. The objects whip around each other hundreds of times per second, moving at speeds approaching light itself. They release more power in gravitational waves than all visible stars in the universe combined. Then they crash together in a final collision, and the gravitational waves carry the news across the cosmos. We detect these final moments as brief signals lasting less than a second. The signal sweeps upward in frequency, creating the characteristic chirp that scientists have learned to recognize. Each detection tells a story of two massive objects completing a dance that began millions of years ago. Fact 31. Black holes can be described by just three properties: mass, spin, and electric charge. This simplicity is remarkable when you think about it. It doesn't matter if the black hole formed from hydrogen or iron, from a blue star or a red one, from a star that had planets, or one that was alone. All that information is lost once the black hole forms. Only these three numbers remain to describe it. This is sometimes called the no-hair theorem, a playful name suggesting that black holes have no extra features or distinguishing characteristics. Two black holes with identical mass, spin, and charge are completely indistinguishable from each other. Everything else about their history is erased, forgotten by the universe. This makes black holes the simplest objects in the universe in some ways, despite being the most extreme. They are pure gravity, stripped of all unnecessary details. A black hole doesn't remember whether it came from a star or formed in the early universe. It doesn't carry information about the star's composition or age. Only mass, spin, and charge survive the collapse. Fact 32. The electric charge of most black holes is probably zero or very close to it. This happens because space contains both positive and negative charges floating around. If a black hole somehow gained a strong positive charge, it would attract negative charges from its surroundings and repel positive ones. These attracted negative charges would fall into the black hole, reducing its charge until it became neutral again. The same thing would happen with a negative charge, just in reverse. Charged particles would quickly neutralize any imbalance. So even though charge is theoretically one of a black hole's properties, in practice nearly all black holes in nature are electrically neutral. Their mass and spin are what really matter for understanding their behavior and effects. Still, physicists study charged black holes mathematically, because the equations reveal interesting features about how electric and gravitational fields interact under extreme conditions. These studies help us understand the underlying physics even if charged black holes don't exist in reality. Fact 33. Neutron stars are the dense remains of exploded stars, but they're not quite black holes. They form when a star's core collapses during a supernova, but stops before becoming a black hole. The collapse is halted by neutron degeneracy pressure, a quantum mechanical effect where neutrons refuse to be squeezed too closely together. This pressure is strong enough to resist gravity if the core isn't too massive. A neutron star might have twice the Sun's mass packed into a sphere only 20 kilometers across, about the size of a city. That's incredibly dense, but not dense enough to create an event horizon. Neutron stars have actual surfaces you could potentially touch, though you'd be instantly crushed by gravity millions of times stronger than Earth's. A teaspoon of neutron star material would weigh billions of tons on Earth. If you added more mass to a neutron star, eventually the neutron pressure would fail, and the star would collapse further into a black hole. The boundary between neutron stars and black holes represents the absolute limit of matter's ability to resist gravity's crushing force. Fact 34. Black holes might create new universes through their singularities, according to some wild but mathematically consistent theories. This speculative idea suggests that the singularity could be connected to a white hole in another universe. A white hole would be the opposite of a black hole, a region where nothing can enter but everything is pushed out. Some theories propose that our entire universe might have emerged from a black hole in a parent universe. When matter collapses into a singularity, it might bounce back in another space, creating a Big Bang there. If true, this would mean universes reproduce like living things, with black holes as the seeds of new cosmic offspring. Each black hole could potentially spawn a new universe with its own physical laws and constants. However, this remains pure speculation without any observational evidence. We have no way to detect white holes or other universes. These ideas exist only in mathematical possibilities and theoretical frameworks. Still, they remind us how strange the universe might be at its deepest levels. Fact 35. The closest supermassive black hole to us lives at the center of our own galaxy, right in the heart of the Milky Way. Sagittarius A star sits roughly 26,000 light-years away from Earth, hidden behind thick clouds of dust and gas. We cannot see it with optical telescopes because the dust blocks visible light, but radio and X-ray observations reveal its presence clearly. Stars near the galactic center orbit this invisible point at tremendous speeds, moving faster than anywhere else in the galaxy. Some stars complete an orbit in just 16 years, moving at thousands of kilometers per second. By tracking these stellar orbits over decades using telescopes, astronomers have precisely measured the central mass. The calculations show something roughly 4 million times the Sun's mass concentrated in a region smaller than Mercury's orbit around the Sun. Nothing but a supermassive black hole fits this description. No cluster of stars or other known object could be that massive and that compact. Fact 36. Black holes can collide with neutron stars, creating hybrid mergers that differ from black hole pairs. When this happens, the black hole's overwhelming gravity tears the neutron star apart before they merge. The neutron star gets stretched and ripped into pieces like taffy being pulled. Some chunks fall into the black hole immediately, while others fly outward into space. This violent destruction creates both gravitational waves and electromagnetic radiation, giving us two ways to observe the event. The electromagnetic signals come from the hot debris, the shredded remains of the neutron star glowing as they heat up. Scientists have detected several such events in recent years, recognized by their distinctive gravitational wave patterns that differ from black hole mergers. These hybrid mergers help us understand what happens when different types of dense objects collide. They also create heavy elements like gold, platinum, and uranium through rapid neutron capture processes. These precious metals were forged in such violent cosmic collisions and scattered into space, eventually becoming part of planets like Earth. Fact 37. The volume inside a black hole's event horizon is difficult to define in any meaningful way. Space and time swap roles once you cross that boundary. The direction toward the singularity becomes a direction in time rather than space. You can no more avoid moving toward the singularity than you can avoid moving into the future in normal space. This means talking about the volume inside becomes problematic because our usual concepts of space don't apply. What we think of as spatial dimensions work differently there. Some calculations suggest the interior of a black hole is infinite in a certain sense, with unlimited space stretching between the horizon and singularity. Others propose finite but curved geometry that twists back on itself. The truth is, we don't know what happens inside because our theories break down completely. We cannot observe it directly, and our equations give strange, contradictory answers. This represents one of the boundaries of human knowledge. Fact 38. Black holes may be connected to dark energy, the mysterious force accelerating the universe's expansion. Some physicists have proposed that black holes could contribute to dark energy through quantum effects we don't yet understand. As black holes evaporate via Hawking radiation over incomprehensible timescales, they might release energy that behaves like dark energy, pushing space apart. However, this idea remains controversial and unsupported by current observations. Another connection might be indirect but still important. Both dark energy and black holes involve extreme conditions where our understanding of physics is incomplete. Studying one might help us understand the other by revealing gaps in our theories. Dark energy makes up about 70% of the universe's total energy, yet we don't know what it is. Black holes challenge our understanding of gravity and quantum mechanics. For now, they remain separate mysteries, both challenging our theories in different ways, both pointing toward physics we have yet to discover. Fact 39. Rotating black holes can theoretically allow shortcuts through space, according to some solutions of Einstein's equations. The spinning creates complex geometry inside and around the event horizon. Mathematical solutions suggest that a rotating black hole might contain a path that avoids the singularity, potentially leading to another region of space or even another universe entirely. These solutions describe what physicists call traversable wormholes. However, these mathematical possibilities likely don't represent physical reality. Small disturbances would probably close any such pathways immediately. Quantum effects might prevent them from forming at all. The mathematics allows these exotic possibilities, but nature may forbid them through mechanisms we don't yet understand. Still, physicists study these solutions because they reveal unexpected features of Einstein's theory and push the boundaries of what's possible. Even if we can never use a black hole for travel, understanding these theoretical possibilities helps us understand gravity itself. Fact 40. Black holes shine brightest when they're actively eating, consuming matter from their surroundings. As material falls toward the event horizon, it heats up through friction and compression, releasing enormous amounts of energy. The faster a black hole consumes matter, the brighter its surroundings glow. Some supermassive black holes devour material equal to several Earths every single day, shining with the power of billions of suns. Others, like our own Sagittarius A star, barely eat anything right now, making them dim and quiet. The brightness can vary dramatically over time. A black hole might be quiet for years or centuries, then suddenly brighten when a star wanders too close and gets torn apart by tidal forces. This temporary brightening, called a tidal disruption event, can make the black hole briefly visible across the universe. These feeding events help astronomers find black holes that were previously invisible. They also tell us about the population of stars around galactic centers. Fact 41. The shadows cast by black holes are larger than their event horizons due to light-bending effects. Light passing near a black hole gets bent by gravity, creating a region of darkness that appears about 2.5 times larger than the event horizon itself. This enlarged shadow is what we see in black hole images like the famous picture from 2019. The shadow's edge corresponds to something called the photon sphere, a region where light can orbit the black hole. Photons travelling at exactly this distance can circle the black hole forever, trapped in endless loops, neither falling in nor escaping. Light just inside this orbit spirals inward and disappears across the horizon. Light just outside manages to escape to space, carrying information about the black hole to distant observers. The photon sphere marks a critical boundary where light's path balances perfectly between escape and capture. It's another invisible boundary, like the event horizon, that shapes how black holes appear to us. Fact 42. Black holes can lose mass through the gravitational waves they emit, especially during mergers. When two black holes orbit closely, each raises tides on the other's event horizon through gravitational interaction. During the final moments before merger, these tides become extreme and violent. Some energy gets converted into gravitational waves rather than being absorbed into the merged black hole. This means the final black hole weighs slightly less than the sum of the two original ones. The missing mass didn't disappear. It became energy carried away by gravitational waves spreading through space. Einstein's famous equation, energy equals mass times the speed of light squared, describes this conversion precisely. About 5% of the total mass might be radiated away during a typical merger, released as gravitational waves in less than a second. This is an enormous amount of energy, equivalent to converting several suns completely into waves. The efficiency of this conversion is actually higher than nuclear fusion in stars. Fact 43. Ancient cultures couldn't have known about black holes through science, yet they often imagined places where things disappeared forever. Myths from around the world told of underworlds, voids, abysses, and monsters that devoured light and souls. The ancient Greeks wrote about Tartarus, a deep abyss beneath the world where the Titans were imprisoned. Norse mythology described Ginnungagap, a primordial void that existed before creation. Hindu cosmology spoke of cosmic dissolution, where everything returns to nothing. These weren't scientific descriptions of black holes, but they show humans have always been fascinated by the idea of cosmic disappearance and eternal darkness. Modern black holes are stranger than any myth or legend. They're real objects that we can study, measure, and predict using mathematics. They obey physical laws we can write down, yet they challenge our understanding just as thoroughly as any legendary monster. Science has given us something more wonderful and mysterious than fiction ever could. Fact 44. The temperature of space itself affects how black holes behave over cosmic time. The universe is filled with cosmic microwave background radiation, the leftover warmth from the Big Bang now cooled to just 3 degrees above absolute zero. Small black holes would emit Hawking radiation hotter than this background temperature, so they would slowly evaporate, losing more energy than they absorb. But large black holes have temperatures far colder than the cosmic background. They absorb more energy from the universe than they emit. This means stellar and supermassive black holes are actually growing very slowly right now, gaining tiny amounts of mass from the background radiation washing over them. They won't start evaporating until the universe cools significantly more, which will take trillions upon trillions of years. Eventually, as the universe expands and cools, the background temperature will drop below even the coldest black hole temperatures. Only then will all black holes begin their slow evaporation into nothing. Fact 45. Black holes preserve certain symmetries and conservation laws perfectly. If you drop a spinning object into a black hole, the black hole's spin changes to conserve angular momentum. The universe keeps track of rotation. Drop in something with mass, and the black hole's mass increases by exactly that amount. Add electric charge, and the charge is preserved precisely. These conservation laws hold even though the object itself is destroyed and seemingly lost forever beyond the event horizon. The black hole remembers only these few properties. Everything else about the fallen object is forgotten. Its composition, its history, its structure, all gone. This selective memory puzzles physicists deeply. Why do black holes preserve some information but destroy the rest? The answer might reveal something fundamental about how information works in our universe, and whether it can truly be destroyed or just transformed. Fact 46. Supermassive black holes and their host galaxies seem to grow together over cosmic time. Galaxies with bigger central bulges have more massive black holes at their centers. This relationship is remarkably tight, suggesting that black holes and galaxies influence each other's development through feedback mechanisms. Perhaps the black hole's jets and winds regulate star formation in the surrounding galaxy, preventing gas from cooling and forming stars. Or maybe gas falling into the galaxy feeds both star formation and black hole growth simultaneously. The relationship is tight enough that astronomers can estimate a galaxy's central black hole mass just by looking at the galaxy's structure and brightness. This connection implies that black holes, despite being tiny compared to galaxies, play crucial roles in galactic evolution and determining what kinds of galaxies form. Fact 47. Miniature black holes could theoretically exist, though we've never found one or seen evidence for them. If black holes formed in the early universe from density variations rather than stellar collapse, some might be quite small. A black hole with the mass of a mountain would be smaller than an atom, tinier than anything we can see with microscopes. One with Earth's mass would fit in your hand comfortably. These tiny black holes would have strong Hawking radiation and would evaporate quickly on cosmic timescales. A black hole with the mass of a large mountain would disappear in a time comparable to the universe's current age. Smaller ones would have evaporated long ago in bright flashes. If any primordial black holes with masses around 1 billion kilograms still exist, they might be evaporating right now. releasing bursts of gamma rays that we could potentially detect with space telescopes. Fact 48. Black holes can act as natural particle accelerators, creating conditions we cannot reproduce on Earth. Material in the accretion disk reaches speeds close to light speed as it spirals inward. Magnetic fields threading through the disk can accelerate particles to even higher energies. Some of the most energetic particles we detect in cosmic rays hitting our atmosphere might originate near black holes. These particles travel through space for millions of years before reaching Earth. When they arrive, they carry energies far beyond what our largest artificial accelerators can achieve. The Large Hadron Collider, our most powerful particle accelerator, reaches energies around 14 trillion electron volts. Some cosmic ray particles have energies millions of times higher. By studying these cosmic rays, scientists gain insights into the extreme physics near black holes. The universe runs experiments that we could never perform in laboratories. Fact 49. Einstein's equations allow for theoretical objects called wormholes, which might be related to black holes in exotic ways. A wormhole would be a tunnel connecting two distant parts of space, potentially allowing shortcuts across the universe. Some mathematical solutions suggest that a rotating black hole's interior could contain a wormhole connecting to another region. However, these theoretical wormholes would be incredibly unstable, collapsing almost immediately unless held open by exotic matter with negative energy density. We've never detected such matter, and it might not exist in nature. Even if wormholes could form somehow, crossing one might be impossible for anything made of normal matter. You would need to move faster than light or survive extreme tidal forces and radiation near the singularity. For now, wormholes remain mathematical curiosities rather than practical travel options, showing what Einstein's equations allow, but nature probably forbids. Fact 50. Black holes teach us about the fundamental limits of knowledge itself. There are questions we cannot answer, not because we lack technology or cleverness, but because the information is fundamentally inaccessible to us. What happens at the singularity right now? What's the exact state inside the event horizon at this moment? These questions might have no answer we can ever verify through observation. Once something crosses the horizon, it cannot send signals back to us. The interior is causally disconnected from our universe. Light cannot escape to tell us what's happening inside. This represents a boundary to science itself, a limit on what we can know. Some knowledge might be permanently beyond our reach, hidden behind horizons we cannot cross. Yet this limitation doesn't stop scientists from theorizing, calculating, and pushing understanding as far as possible. We can still learn about black holes indirectly, by studying what they do rather than what they are inside, by measuring their effects on the universe around them. Fact 51. The fabric of space itself can be thought of as something physical near a black hole. Einstein showed us that space isn't just empty nothingness. It's a real thing that can bend, stretch, and curve. Near a black hole, space curves so sharply that it almost folds in on itself. Imagine a rubber sheet pulled down by a heavy weight, but stretched so far that the sheet nearly tears. This curvature affects everything nearby. Light follows the curves, matter follows the curves, even time flows differently along these bent paths. The closer you get to a black hole, the more dramatic the curvature becomes. At the event horizon, space curves so completely that all directions point inward. There's no path leading outward anymore. This isn't just mathematical abstraction. The curvature is real and measurable. We detect it through gravitational lensing and the orbits of nearby objects. Black holes are places where space itself becomes an active player in the cosmic drama, not just a stage where events unfold. Fact 52. Some black holes might be older than most stars in the universe. If primordial black holes formed shortly after the Big Bang, they would have existed for nearly the entire history of the cosmos. These ancient objects would have witnessed the universe's evolution from a hot, dense state to the cool, expanded cosmos we see today. They would have been around when the first stars ignited, when the first galaxies assembled, when heavy elements were forged. A primordial black hole would be a time capsule from the earliest moments of existence. Regular stellar black holes are much younger, formed from stars that lived and died. The oldest stellar black holes might be 10 or 12 billion years old, created when the universe was still young. But primordial ones could be 13.8 billion years old, almost as old as time itself. These ancient objects would have absorbed matter from different eras, each edition a layer recording cosmic history. Finding and studying primordial black holes would give us direct evidence about conditions in the newborn universe. Fact 53. Black holes can wander through galaxies like cosmic nomads. Most supermassive black holes sit at galactic centers, but smaller ones move freely through space. When a star explodes and creates a black hole, the explosion might not be perfectly symmetric. One side might blast out more material than the other, giving the newly formed black hole a kick, like a rocket. This kick can send the black hole flying through the galaxy at hundreds of kilometers per second. These wandering black holes travel through space, potentially encountering other stars and systems. If one passed near our solar system, we might not even notice unless it came very close. Most of space is empty, so these wanderers rarely collide with anything. They're invisible nomads, detectable only if they happen to steal gas from a passing star, or if we notice their gravitational effects on nearby objects. Some might even escape their home galaxies entirely, ejected into the void between galaxies to drift alone forever. Fact 54. The merger of two black holes creates a new black hole that rings like a bell. After the collision, the combined black hole isn't perfectly smooth immediately. It's distorted, with bulges and ripples on its event horizon. These distortions settle down quickly, radiating away as gravitational waves. The process is called ring down because it resembles a bell ringing after being struck. The frequency and damping of these oscillations depend on the final black hole's mass and spin. By analysing the ring down signal, scientists can measure these properties precisely. Different masses and spins produce different tones. It's like identifying a bell by listening to its ring. This ring down happens incredibly fast, lasting only milliseconds for stellar black holes. But in that brief moment, we learn about the properties of the newly merged object. The universe is full of these cosmic bells ringing out their properties, and we've learned to listen and understand their songs. Fact 55. Black holes might explain dark matter, one of the universe's biggest mysteries. Dark matter is invisible substance that doesn't emit or absorb light, yet it makes up most of the matter in galaxies. We know it exists because galaxies rotate faster than they should based on visible matter alone. Something unseen is providing extra gravity. One possibility is that dark matter consists of primordial black holes formed in the early universe. These would be gravitationally influential but optically invisible, matching dark matter's properties. However, observations have ruled out many mass ranges for primordial black holes. If they exist, they must be either very light or very heavy to avoid detection so far. Most scientists think dark matter is probably exotic particles we haven't discovered yet, not black holes. Still, the possibility remains open for certain mass ranges. Finding or ruling out primordial black holes helps narrow down what dark matter could be. Fact 56. When a star gets too close to a black hole, tidal forces rip it apart in an event more violent than a supernova. The side of the star facing the black hole feels much stronger gravity than the far side. This difference stretches the star like taffy until it breaks apart completely. Half the stellar debris falls into the black hole while the other half gets flung outward into space. The infalling material heats up tremendously, creating a bright flare that can outshine the entire galaxy for weeks or months. Astronomers have observed dozens of these tidal disruption events. Each one provides a chance to study black holes that were previously quiet and invisible. The disrupted star was probably orbiting peacefully for millions of years before wandering slightly too close. One small deviation in its orbit sealed its fate. These events remind us that black holes are patient hunters, waiting for prey to come close enough. Fact 57. Black holes have no solid surface to land on. If you could somehow survive the journey to the event horizon and beyond, you wouldn't hit anything. You would just keep falling. The singularity at the center isn't a surface either. It's a point where density becomes infinite, and our understanding breaks. There's nothing to stand on, nothing to touch. Just increasingly strong gravity pulling you inward and stretching you longer. This can be hard to imagine because every object we encounter in daily life has a surface. Planets have surfaces, stars have surfaces, though they're made of gas. Even neutron stars have surfaces, incredibly dense but real. Black holes don't. They're fundamentally different from other objects. The event horizon isn't a surface but a boundary in space. Cross it and you're in a region where different rules apply. This surfaceless nature makes black holes unique in the cosmos. Fact 58. The study of black holes combines the two greatest theories in physics, general relativity and quantum mechanics. General relativity describes gravity and how mass curves space and time. It works perfectly for large objects like planets, stars, and black holes. Quantum mechanics describes the behavior of tiny particles and forces at atomic scales. It works perfectly for atoms, electrons, and photons. But these two theories don't work well together. They give contradictory predictions when applied to the same situation. Black holes force us to confront this problem because they're places where both theories should apply. The singularity is tiny like a quantum particle, but has enormous mass like a relativistic object. Hawking radiation involves quantum effects at the event horizon of a massive gravitational object. Understanding black holes completely requires a unified theory combining both frameworks. This theory, often called quantum gravity, remains one of physics' greatest unsolved challenges. Fact 59. Black holes can exist in clusters, with multiple black holes orbiting each other in complex patterns. Dense star clusters at galactic centers might contain dozens or hundreds of stellar black holes. These black holes formed from massive stars in the cluster and remained gravitationally bound to the system. Over time, they sink toward the cluster's center through gravitational interactions. Eventually, multiple black holes might orbit each other in a small region. Sometimes pairs collide and merge. Other times, three or more black holes interact, with one getting ejected at high speed. These interactions create a rich environment for gravitational wave production. Clusters might be factories for black hole mergers, producing events we can detect. Understanding how black holes behave in clusters helps us predict what LIGO and similar detectors should observe. It also tells us about the environment at galactic centers where conditions are extreme. Fact 60. The information paradox has inspired new ideas about how reality works. If black holes destroy information, then the future cannot be predicted from the past, violating fundamental principles of physics. To avoid this, some scientists propose that information isn't stored inside the black hole but on its surface. The event horizon might act like a hard drive, encoding every detail about what fell in. This idea leads to the holographic principle, suggesting our three-dimensional universe might be a projection from information stored on a two-dimensional boundary. It's as if we're living inside a cosmic hologram. Other proposals suggest information might leak out through Hawking radiation in subtle ways we don't yet understand. Or perhaps information escapes through quantum tunneling or wormholes. Each solution sounds strange, but the paradox forces us to reconsider basic assumptions about space, time, and information. Black holes push physics into new territory. Fact 61. Binary black holes spiral toward each other in a beautiful cosmic dance. When two black holes orbit closely, they gradually move closer together over millions of years. Gravitational waves carry energy away from the system like ripples spreading from a spinning object. With less energy, the orbit shrinks. The black holes move faster to conserve angular momentum. This creates a feedback loop where they spiral inward faster and faster. The final moments happen incredibly quickly. Within the last second, the black holes complete hundreds of orbits, whipping around each other at substantial fractions of light speed. Then they merge in a violent collision that releases more power than all stars combined. The gravitational wave signal from this spiral sweeps upward in frequency, creating the characteristic chirp scientists listen for. Each chirp tells a story of two massive objects completing a dance that began when the universe was younger. Fact 62. Not all black holes form from stars. Supermassive black holes at galactic centers are too large to have formed from single stars. Even the biggest stars produce black holes only dozens of times the Sun's mass, not millions or billions of times. So how did supermassive black holes grow so large? Several theories exist. Perhaps they started as stellar black holes and fed on gas for billions of years, growing gradually. Or maybe they formed directly from collapsing gas clouds in the early universe, beginning with much larger masses. Another possibility involves mergers. When galaxies collide, their central black holes eventually merge, creating larger ones. Over cosmic time, through many mergers and steady feeding, black holes could reach supermassive sizes. We observe supermassive black holes in the early universe, less than 1 billion years after the Big Bang. They somehow grew enormous very quickly. which challenges our understanding. The origin of supermassive black holes remains an active research area. Fact 63. The nearest stellar black hole to Earth might be closer than we think. Astronomers estimate that thousands of stellar black holes exist within our galaxy, mostly invisible unless they're actively feeding. Statistical models suggest one might be within a few hundred light years of us. We simply haven't found it yet because it's dark and quiet. If such a nearby black hole had a companion star, we might detect it through the star's motion. The star would wobble as it orbited the invisible partner. Several candidate systems exist where stars appear to orbit massive unseen objects. As our telescopes improve and we survey more stars carefully, we'll likely discover black holes closer than any we currently know. This isn't dangerous. Even a black hole 100 light-years away poses no threat to Earth. Space is so vast that close in astronomical terms still means incomprehensibly far by human standards. Fact 64. Black holes can spin at tremendous rates, approaching but never exceeding the speed of light at their event horizons. The maximum possible spin is determined by the black hole's mass and the requirement that the event horizon can't move faster than light. This limit is called the extremal spin. In practice, most black holes probably spin below this maximum because friction and absorbed material tend to slow them down over time. However, black holes formed from mergers can spin very fast. If two black holes merge just right, with their spins aligned properly, the resulting black hole can have a spin close to the maximum. Fast-spinning black holes have several interesting properties. Their ergospheres are larger, allowing more energy extraction. Their event horizons are slightly smaller than non-spinning ones of the same mass, and they drag space around them more dramatically, creating stronger frame dragging effects. Fact 65. Every galaxy merger likely results in a black hole merger eventually. Most large galaxies have supermassive black holes at their centers. When two galaxies collide, which happens regularly over cosmic time, the galaxies merge into a single larger galaxy. The two central black holes don't merge immediately. First, they orbit within the merged galaxy, separated by thousands of light years. Gravitational interactions with stars and gas cause them to lose energy and spiral closer together. This process can take hundreds of millions of years. Eventually, they get close enough that gravitational waves dominate, and they spiral rapidly to merger. The resulting gravitational wave signal is too low in frequency for LIGO to detect, but falls perfectly in the range for planned space-based detectors. These supermassive black hole mergers are among the most energetic events possible, releasing more energy in gravitational waves than millions of supernovae combined. Fact 66. Hawking's work on black hole thermodynamics revealed deep connections between gravity, quantum mechanics, and information. He showed that black holes have entropy proportional to their surface area, not volume. This was surprising because entropy usually depends on volume for ordinary objects. A cup of hot coffee has more entropy than a cold one because the molecules move faster, exploring more possible states. For black holes, everything depends on area. This led to ideas about information being stored on surfaces rather than in volumes. Hawking also discovered that black holes have temperature and emit radiation, meaning they're thermodynamic objects. They can heat up, cool down, and exchange energy with surroundings. These insights suggested that black holes aren't separate from thermodynamics, but examples of it. The laws of black hole mechanics mirror the laws of thermodynamics precisely, hinting at deep underlying unity in physics. Fact 67. Intermediate mass black holes remain mysterious objects we rarely detect. These black holes, with masses between 100 and 100,000 suns, don't fit easily into formation theories. They're too heavy to form from single stars, but too light to be the supermassive ones at galactic centers. We've found only a handful of strong candidates. They might form in dense star clusters where many stars collide and merge. Or perhaps they're the seeds that eventually grow into supermassive black holes. Some might be leftovers from the early universe, neither stellar nor supermassive, but something in between. Recent gravitational wave detections have found black holes in this mass range, suggesting they're more common than we thought. Understanding how these intermediate objects form and evolve will help complete our picture of black hole populations. They fill a gap between stellar and supermassive types. Fact 68. The no-hair theorem states that black holes are remarkably simple objects externally. No matter how complex the original star was, the resulting black hole has only three properties. Its mass tells you how much stuff fell in. Its spin tells you how much angular momentum it has. Its charge tells you the electrical balance. Everything else is lost. The star's chemical composition, magnetic fields, surface features, interior structure, all vanish. Two black holes with identical mass, spin and charge are indistinguishable even in principle. This simplicity contrasts sharply with stars, which have many observable properties. You can measure a star's temperature, composition, age, magnetic field, rotation at different depths, and much more. Black holes erase all this complexity. They're bald, in the theorem's terminology, having no hair or distinguishing features. This makes them simple to describe mathematically, but also mysterious. Where did all that information go? Fact 69. Accretion disks around black holes can launch winds that blow throughout entire galaxies. These winds consist of hot gas, accelerated by radiation pressure and magnetic fields near the black hole. The winds carry energy outward at thousands of kilometers per second. When they slam into surrounding gas clouds, they heat the gas and prevent it from cooling and forming stars. This provides a feedback mechanism controlling galaxy growth. Without this feedback, galaxies would form stars too quickly and run out of gas. The central black hole regulates star formation throughout the galaxy, even though the black hole itself is tiny compared to the galaxy. This is one way black holes influence their cosmic neighborhoods beyond just gravity. The winds also carry heavy elements forged near the black hole, distributing them throughout the galaxy. This enriches the material from which future stars form. Fact 70. Black holes might allow tests of general relativity in extreme conditions. Einstein's theory has passed every test so far in weaker gravitational fields. But near black holes, gravity becomes so strong that subtle deviations from Einstein's predictions might appear. Alternative theories of gravity make slightly different predictions about black hole properties. The shape of the shadow, the frequency of gravitational waves, the details of the inspiral all depend on exactly how gravity works. By measuring these properties precisely, we test whether Einstein was completely right or whether corrections are needed. So far, observations match Einstein's predictions remarkably well. Black holes behave exactly as his equations predict, but more precise measurements might reveal tiny deviations pointing toward deeper theories. Black holes are natural laboratories for testing physics under conditions we cannot create artificially. Fact 71. The cosmic censorship hypothesis suggests that singularities are always hidden behind event horizons. This hypothesis, proposed by Roger Penrose, states that nature prevents naked singularities from forming. A naked singularity would be a point of infinite density visible to the universe, not hidden inside a black hole. If naked singularities existed, they could violate causality and create paradoxes. The cosmic censorship hypothesis says this doesn't happen. Whenever matter collapses to form a singularity, an event horizon forms around it first, hiding it from view. This keeps the universe predictable and prevents paradoxes. However, the hypothesis isn't proven. It's a conjecture supported by many examples but not established as absolute law. Some exotic scenarios in theory allow naked singularities, though they require unrealistic conditions. Whether cosmic censorship always holds remains an open question in theoretical physics. Fact 72. Black holes can be used as cosmic particle detectors. High-energy particles spiraling in the magnetic fields near a black hole emit radiation with characteristic patterns. By studying this radiation, we learn about particle physics in conditions we cannot replicate on Earth. The magnetic fields near black holes can be millions of times stronger than anything we create artificially. Particles accelerate to energies beyond our most powerful accelerators. These particles then interact, producing cascades of other particles. Some of these interactions might involve physics beyond the standard model of particle physics. Black holes become natural experiments in high-energy physics. The universe provides the laboratory. We just need to observe carefully and interpret correctly. This connects black hole astronomy with particle physics, two fields that might seem unrelated but actually inform each other. Fact 73. Supermassive black holes can have masses billions of times greater than our Sun. The largest known black holes exceed 10 billion solar masses. These monsters lie at the centers of the most massive galaxies. Their event horizons span distances larger than our solar system. If one replaced our Sun, the event horizon would extend beyond Jupiter's orbit. Despite this enormous size, the black hole would still be incredibly dense. No ordinary matter can achieve such densities without collapsing. These ultramassive black holes probably grew through countless mergers and steady feeding over billions of years. Each galaxy merger added mass. Each passing star cloud that ventured too close contributed material. Over time, through patient accumulation, these black holes reached almost unimaginable sizes. Yet even these giants follow the same basic physics as stellar black holes. The equations scale smoothly from small to large. Fact 74. Gravitational waves from black hole mergers have opened a new window on the universe. Before their detection, we observed the cosmos only through electromagnetic radiation and particles like neutrinos and cosmic rays. Gravitational waves add a completely new sense. They carry information that light cannot. They pass through dust clouds that block optical telescopes. They reveal events involving dark objects that emit no light. The first detection in 2015 confirmed that black holes exist and merge as predicted. Subsequent detections have found black holes in unexpected mass ranges, taught us about how black holes spin, and tested Einstein's theory in new ways. Future detectors will observe thousands of mergers per year, creating a census of black hole populations throughout the universe. Gravitational wave astronomy has transformed from theoretical possibility to practical reality in less than a decade. Fact 75. The universe might be filled with a background hum of gravitational waves from all past black hole mergers. Each merger sends waves in all directions. Waves from billions of mergers throughout cosmic history overlap and combine. This creates a stochastic background, like the sound of ocean waves from countless ripples. The signal is too faint and random for current detectors to identify individual events, but we might detect the combined noise. This background would tell us about the overall rate of mergers throughout history. It carries information about black hole populations in the distant past. Future experiments hope to detect this gravitational wave background. It would be another confirmation of general relativity and another tool for understanding cosmic history. The universe constantly rings with gravitational echoes from ancient collisions. Fact 76. Black holes challenge our understanding of cause and effect in ways that make philosophers and physicists equally uncomfortable. In normal physics, causes precede effects in a clear sequence. You throw a ball, then it flies through the air. You light a match, then fire spreads. But inside a black hole, time and space swap roles in a way that makes causality strange and almost incomprehensible. The singularity lies in your future, not in a particular location you might avoid. You cannot avoid reaching it any more than you can avoid tomorrow arriving, or the next minute passing. This temporal inevitability replaces spatial trapping. Outside the horizon, we think of being trapped as unable to move to certain places, like being locked in a room with walls. Inside, you're trapped in time itself, unable to prevent a future event from occurring. This distinction matters deeply for understanding what falling into a black hole really means. It's not like being locked in a room where you can pace back and forth. It's like being forced to age, to experience future moments whether you want to or not. The singularity is your destiny once you cross the horizon, as unavoidable as death itself. Every possible path forward leads there. There are no detours, no alternate routes. The future becomes singular. Fact 77. Some scientists propose that black holes could be portals to other universes, though this remains highly speculative and unsupported by evidence. Certain solutions to Einstein's equations allow mathematical connections between different regions of space-time, structures that exist on paper even if nature forbids them. These connections, called Einstein-Rosen bridges or wormholes, might theoretically link our universe to another cosmos entirely, a separate bubble of space-time with its own stars and galaxies. However, these solutions require exotic conditions that probably aren't physically realistic. Quantum effects would likely destroy any bridge before it became traversable, tearing it apart at the quantum level. The structure would be unstable, collapsing faster than light could cross it. Still, the mathematics permits these possibilities, showing that general relativity allows stranger things than we usually imagine. The equations contain hidden possibilities that emerge only when you explore unusual conditions. Even if black holes aren't portals in reality, studying these theoretical possibilities helps physicists understands space-time's flexibility and structure. The equations contain surprises that reveal their inner workings. Exploring them mathematically, even when they don't represent reality, teaches us about the theory's structure and limitations. Sometimes impossible scenarios reveal important truths about what is possible. They show us the boundaries of physical law. Fact 78. Black hole jets can stretch across millions of light years, making them the largest structures created by single objects in the entire universe. These jets shoot out from regions near the black hole's poles, launched by complex interactions between magnetic fields and rotating material. They carry energy and particles at nearly light speed, creating narrow beams that pierce through space. They pierce through the surrounding galaxy and continue into intergalactic space, creating giant lobes of radio emission where they slam into thin gas between galaxies. The lobes glow in radio wavelengths, revealing the jet's extent. Some jets maintain their narrow structure across these incredible distances, staying focused like cosmic laser beams. The beam might be only a few hundred light-years wide but millions long. The mechanisms keeping jets collimated over such distances involve magnetic fields and particle interactions we don't fully understand. Somehow the magnetic field prevents the jet from spreading out as it travels. These jets affect galaxy evolution in profound ways. They heat surrounding gas and prevent it from cooling, which suppresses star formation. They also trigger star formation in other regions by compressing gas clouds. They redistribute energy across vast regions, influencing cosmic structure on the larger scales. A supermassive black hole weighing millions of suns can affect regions, millions of light years across through these jets, reaching far beyond its own gravity. Fact 79. The mathematics describing black holes includes complex numbers, abstract geometry, and tensor calculus that seem far removed from physical reality to most people. Yet these mathematical tools make precise predictions that observations confirm with remarkable accuracy. The metric tensor describing spacetime curvature around a black hole involves equations that would fill many pages if written out completely. Solving them requires sophisticated techniques from differential geometry and tensor calculus, subjects most people never study. The calculations involve indices running over 4 dimensions, covariant derivatives, and contractions that require careful bookkeeping. Most people cannot follow the mathematics in detail without years of specialized training. Yet the results are concrete and testable in the real world. The equations predict exactly how light bends around massive objects, how orbits behave in strong gravity, what gravitational waves look like when black holes merge. Every prediction tested so far has matched observations within experimental uncertainties. This demonstrates mathematics' extraordinary power to describe nature accurately, even when the math itself seems abstract and divorced from everyday experience. Black holes exist at the intersection of pure mathematics and physical reality, showing that the universe operates according to mathematical principles we can discover and verify. The universe speaks mathematics, and we've learned to understand its language. Fact 80. Ancient light from the early universe has passed by countless black holes on its journey to us across billions of years. The cosmic microwave background, radiation released 380,000 years after the Big Bang, has travelled for over 13 billion years before reaching our telescopes today. During this incredibly long journey, some of it passed near black holes that existed throughout cosmic history, getting gravitationally lensed and slightly altered. The paths of photons bent around massive objects. By studying these subtle distortions in the cosmic microwave background, scientists can learn about black holes that existed in the distant past, objects that formed billions of years ago. This technique provides another way to search for primordial black holes formed in the early universe. If many small black holes formed in the first moments after the Big Bang, they would leave distinctive patterns in the background radiation, specific distortions that would reveal their presence. So far, observations place strict limits on how many primordial black holes could exist without creating distortions we don't see. The ancient light carries information about every era it passed through, including evidence about black holes throughout cosmic history. It's a cosmic messenger that witnessed the universe's evolution. Fact 81. Black holes emit almost no radiation, except for the theoretical Hawking radiation, which remains undetected because it's so incredibly faint. This makes them the darkest objects possible in the universe, darker even than the darkest paint humans have created. A black hole absorbs any light that hits it, reflecting nothing back into space. Its temperature is far below that of surrounding space for any stellar or supermassive black hole we've observed. The cosmic microwave background has a temperature of about 3 degrees above absolute zero, while most black holes have temperatures far lower. This extreme darkness means black holes represent the closest thing to absolute nothingness, while still being something real and massive. They're present but invisible, influential through gravity but optically dark. This quality gives them their name and much of their mystique. In a universe filled with stars and galaxies radiating light across the spectrum, black holes are zones of absolute silence and darkness. They absorb the universe's energy without giving much back, at least on timescales we can measure or observe. Only over periods vastly longer than the current age of the cosmos, trillions upon trillions of years, would Hawking radiation become significant enough to detect. Until then, they remain dark sentinels scattered throughout the universe. Fact 82. The concept of a black hole emerged from pure mathematics before anyone believed they existed physically in nature. In 1916, just months after Einstein published general relativity, physicist Karl Schwarzschild found an exact solution to Einstein's equations describing spacetime around a spherical mass. He was serving in the German army during World War I when he worked out these equations. This solution predicted a radius where strange things happened, though Schwarzschild himself didn't interpret it as representing a physical object. For decades afterward, physicists debated whether these mathematical curiosities could exist in nature or were just artifacts of the equations. Einstein himself strongly doubted they could form, writing papers arguing that nature would prevent such extreme collapse. Most scientists thought something would prevent complete collapse into these strange objects. Only in the 1960s did theoretical work by physicists like John Wheeler and Roger Penrose, combined with astronomical observations of quasars and X-ray sources, convince physicists that black holes probably existed. The mathematics predicted reality before reality was observed, a common pattern in physics showing that equations sometimes understand the universe better than human intuition does. Mathematics led the way, and reality followed. Fact 83. Black holes can have atmospheres of sorts, regions of hot gas and plasma surrounding them in complex structures. This material hasn't crossed the event horizon yet, but orbits in the accretion disk or corona above it, trapped in the black hole's gravitational field. Temperatures in these regions reach millions or billions of degrees, hot enough to strip atoms of all their electrons and create fully ionized plasma. This plasma emits X-rays and other high-energy radiation that telescopes can detect across vast distances. The conditions are more extreme than anywhere else in the universe, except perhaps the Big Bang itself, or the cores of the most massive stars. Particles collide at enormous energies, creating cascades of secondary particles. Magnetic fields twist and snap, releasing energy suddenly. Radiation pressure pushes against gravity in a constant struggle. These atmospheres are natural laboratories for extreme physics that we could never recreate on Earth. By observing the radiation they emit, we learn about conditions near the event horizon that we can study no other way. Different patterns of flickering and variability in the X-ray emission tell us about the black hole's spin, mass, and feeding rate. Sometimes the brightness changes in milliseconds, revealing dynamics happening close to the event horizon where material orbits incredibly fast. Fact 84. If you could somehow hover just outside a black hole's event horizon using powerful rockets, you would age much faster than people far away from the gravitational field. Time dilation works both ways simultaneously, creating a strange symmetry. From your perspective near the black hole, time flows normally. Your watch ticks normally. Your heart beats normally. But if you could look back at the distant universe through a telescope, you would see it evolving rapidly. Like watching a movie in fast-forward mode, stars would be born and die quickly. Galaxies would collide and merge. The universe would age before your eyes, centuries passing in what felt like hours to you. Meanwhile, people watching you from far away with telescopes would see you moving in slow motion, frozen near the horizon like a statue. They would see your clock ticking very slowly, your movements glacial. This time, dilation effect becomes infinite at the event horizon itself. An outside observer would see you take forever to cross it, approaching asymptotically but never quite reaching it. Though from your viewpoint, The crossing happens in finite time, perhaps just a few seconds depending on the black hole's mass. This asymmetry in perceived time flow shows how profoundly relative time truly is. There is no universal clock. Time passes differently in different gravitational fields. Fact 85. Black holes might preserve information through quantum entanglement with the radiation they emit over immense timescales. Entanglement is a quantum phenomenon where two particles remain mysteriously connected regardless of the distance separating them. Measuring one instantly affects the other, even across light years. Some physicists propose that particles falling into a black hole remain entangled with particles in the Hawking radiation emitted later. This entanglement could encode information about what fell in, allowing the information to escape gradually as the black hole evaporates over trillions of years. The details of how this mechanism works remain unclear and highly controversial. The process would be incredibly subtle, not obvious from studying the radiation directly with any simple measurement. But it might resolve the information paradox by showing that information isn't truly destroyed, just encoded in complex correlations between particles that seem random individually but contain hidden patterns. This idea connects black holes to quantum information theory, a modern field studying how information behaves at fundamental levels, how it's stored in quantum states, and whether it can ever truly be destroyed. The marriage of black hole physics and quantum information theory has become one of the most active research areas in theoretical physics. Fact 86. The largest black holes grow primarily by merging with other black holes and accreting gas rather than swallowing individual stars. Individual stars don't contribute much mass because even large stars weigh far less than supermassive black holes that already weigh millions of suns. A star like our Sun weighing 1 solar mass barely affects a black hole weighing 4 million solar masses, adding only a tiny fraction to its total. But when galaxies merge, which happens regularly throughout cosmic history, their central black holes eventually combine after spiraling together for millions of years. This merger can double or triple the mass in one dramatic event lasting seconds. Similarly, when cold gas flows toward the galactic center through various mechanisms, the black hole can consume large amounts steadily over millions of years. These processes built the supermassive black holes we observe today. Over billions of years, through many mergers and steady feeding episodes, black holes grew from perhaps stellar mass seeds to the giants containing billions of solar masses. The growth history of black holes mirrors the assembly history of galaxies themselves, the two evolving together in a cosmic partnership. Fact 87. Detecting black holes requires clever indirect methods since they emit no light directly from their event horizons. Astronomers have developed multiple techniques, each revealing different populations. They look for stars orbiting invisible objects, their motion revealing the hidden mass. By tracking a star's orbit for years, they calculate the central mass and determine whether a black hole must be present. Gas heating up as it spirals inward toward the black hole emits X-rays we can detect with space telescopes, creating bright X-ray sources. Gravitational lensing bends background light in distinctive patterns when a black hole passes between us and distant stars. Gravitational waves from mergers carry unmistakable signals that match theoretical predictions precisely. Each method has strengths and limitations that complement each other. X-ray observations find actively feeding black holes, but miss quiet ones that aren't consuming material. Gravitational waves detect mergers but not solitary black holes drifting alone. Orbital measurements work only for nearby objects where we can track stellar motion over years or decades. By combining multiple methods, astronomers build a complete picture of black hole populations throughout the universe. Each detection confirms these objects exist in nature and helps us understand their properties, distribution, and how they formed. Fact 88. Black holes are among the most efficient engines in the universe for converting mass into energy through various physical processes. When matter falls into a spinning black hole, up to 40% of its rest mass can be converted to energy through processes involving the black hole's spin and magnetic fields threading through the accretion disk. This efficiency far exceeds nuclear fusion in stars, which converts less than 1% of mass to energy, or nuclear fission in reactors, which is even less efficient. A black hole power plant, if one could ever be built by an advanced civilization, would be the ultimate energy source, far surpassing any other technology. Of course, building such a thing is pure science fiction and likely impossible for practical reasons. But the theoretical efficiency shows how powerful black hole accretion processes truly are. Quasars and active galactic nuclei shine so brightly across billions of light years because this efficient conversion turns infalling matter into tremendous radiation. A region smaller than our solar system can outshine 1 trillion stars. This efficiency helps explain how relatively small regions around black holes can outshine entire galaxies containing hundreds of billions of stars, making them visible across cosmological distances. Fact 89. The study of black holes has progressed from mathematical curiosity to observational science in just a few decades of rapid advancement. In the 1960s, black holes were purely theoretical possibilities debated among physicists with no observational evidence. By the 1970s, X-ray observations found strong candidates like Cygnus X1, a system where a visible star orbits an invisible massive companion. The 1990s and 2000s brought observations of stars orbiting Sagittarius A star at the Milky Way's center, proving a supermassive black hole existed there through careful tracking of stellar orbits. In 2015, LIGO detected gravitational waves from merging black holes for the first time, opening an entirely new window on the universe. In 2019, the Event Horizon Telescope imaged a black hole's shadow directly, creating a picture of the unseeable. Each decade has brought new capabilities and discoveries that were impossible before. This rapid progress shows how technology enables science to advance. Better detectors, bigger telescopes, more sensitive instruments, advanced computers for data processing. All expanded what we could observe and measure. Black holes went from speculative theory to confirmed reality to objects we routinely study and even photograph. The pace of discovery continues accelerating as new instruments come online. Fact 90. Black holes rotate at different speeds depending on their formation history and how they've been fed over time. Some spin rapidly, rotating hundreds of times per second at their event horizons, approaching the maximum spin allowed by physics. Others spin slowly or barely at all, perhaps having been spun down by accretion from random directions. The spin rate affects the black hole's properties significantly in measurable ways. Fast-spinning black holes have smaller event horizons for the same mass compared to slow-spinning ones, making them more compact. They drag space around them more strongly, creating larger ergospheres where nothing can remain stationary. Their ergospheres extend further from the horizon, making the effects more pronounced. Measuring a black hole's spin tells us about its history and how it formed. Did it form from a single collapsing star that was already spinning? Or did it form from mergers of multiple black holes whose spins partially cancelled? Has it been accreting steadily from one direction, which would spin it up over time, or from random directions, which would average out to little net spin? Spin measurements help reconstruct individual black holes' histories and test formation theories, connecting observations to theoretical models. Fact 91. The entropy of a black hole is enormous, vastly larger than any normal object of comparable mass. Entropy measures disorder and the number of possible microscopic states consistent with what we observe macroscopically. A black hole's entropy is proportional to its surface area measured in Planck units, which are incredibly tiny. For a solar mass black hole, this entropy exceeds the entropy of the Sun itself, despite the black hole being far smaller in volume. For supermassive black holes, the entropy is almost incomprehensibly large, larger than anything else in the universe. This huge entropy suggests that black holes have incredibly many internal states, even though they appear simple externally with just 3 observable properties. Quantum gravity theories try to account for this entropy by proposing what these internal states might be at the microscopic level. String theory, for example, suggests they correspond to different configurations of strings and branes in higher dimensions. Loop quantum gravity proposes they arise from quantum geometry of spacetime itself. Understanding black hole entropy might be key to developing a complete theory of quantum gravity that unites Einstein's classical theory with quantum mechanics. The entropy provides a target that any successful theory must reproduce. Fact 2. Black holes can exist in isolation, wandering through empty intergalactic space without companions or nearby material to interact with. These isolated black holes are extremely difficult to detect because they neither emit light nor gravitationally affect visible objects we can observe. They're invisible wanderers, detectable only through rare gravitational lensing events when they happen to pass between us and a background star. The background star would briefly brighten as the black hole's gravity focused its light toward us like a lens, creating a characteristic light curve. Several searchers look for such micro-lensing events by monitoring millions of stars simultaneously, looking for the telltale brightening pattern. By measuring the duration and characteristics of the brightening, scientists can estimate the lensing object's mass and distance. If it's in the black hole mass range and emits no light of its own, it's probably an isolated black hole drifting alone. These objects remind us that much of the universe remains hidden from direct observation, detectable only through gravity's subtle effects on light passing nearby. The universe likely contains many isolated black holes we've never detected. Fact 93. The geometry of space-time around a black hole is described by the Schwarzschild metric for non-rotating black holes, or the more complex Kerr metric for rotating ones. These metrics are mathematical descriptions of how distances and times are measured near the black hole, how the fabric of space-time itself is curved. They tell you how much clocks slow down at different distances, how paths curve through space, how much energy particles need to maintain certain orbits. The metrics reduce to flat Minkowski space-time far from the black hole, showing that Einstein's theory smoothly connects normal space to extreme conditions without discontinuities. Close to the black hole, the metrics reveal dramatic curvature with significant deviations from flat space. Radial distances stretch, meaning you have to travel further than you'd expect to increase your distance from the center. Circular paths shorten. Time dilates severely, with clocks running slower and slower. These metrics have been tested extensively through observations of stellar orbits around Sagittarius A star, gravitational waves from mergers, and light bending near massive objects. Every test confirms that Einstein's equations accurately describe reality, even under the most extreme conditions we can observe, giving us confidence that the theory is correct. Fact 94. Black holes might eventually dominate the universe's mass in the far future, if current cosmological models are correct. As stars exhaust their fuel over trillions of years, more black holes form from stellar collapse, adding to their population. Existing black holes slowly grow by absorbing nearby material and merging with each other whenever they encounter partners. Meanwhile, ordinary matter gradually gets consumed by black holes, or locked into cold, dark objects like brown dwarfs and white dwarfs that emit no significant light. In trillions of years, most matter might be either inside black holes or in cold remnants incapable of forming new stars because all the gas has been used up. The universe would become progressively darker and emptier, with black holes as the primary massive objects and the most notable structures. Then, over incomprehensibly longer timescales measured in Google years or more, Hawking radiation would cause even these black holes to evaporate completely, dissolving back into radiation. The universe would end up as thin radiation and elementary particles, with no complex structures remaining anywhere. This far future scenario shows that black holes aren't eternal, despite seeming permanent on human or even stellar timescales. Everything that forms eventually dissolves. Fact 95. Studying black holes teaches us about the universe's fundamental nature in ways few other objects can. They sit at the intersection of our deepest theories about reality. General relativity describes their formation and properties, making precise predictions about their behavior. Quantum mechanics predicts they emit radiation and have entropy, connecting them to information theory. Thermodynamics applies to their behavior, with black holes having temperature and obeying laws parallel to thermodynamic laws. Information theory connects to the information paradox and questions about what happens to information. Every major framework in modern physics touches black holes somehow, making them unifying objects. This makes them ideal testing grounds for theoretical ideas and proposed new physics. When theories make different predictions about black holes, observations can determine which theory better describes reality. Black holes also reveal gaps in our understanding clearly. The information paradox and singularity problem show where current theories fail and new physics is needed. Resolving these issues will likely require new physics beyond what we currently know, perhaps a quantum theory of gravity. Black holes guide us toward deeper understanding of nature's laws. Fact 96. The smallest possible black hole that could form from stellar collapse would have a mass around 3 times the Sun, setting a lower limit. Below this threshold, neutron degeneracy pressure prevents complete collapse into a black hole. The core becomes a neutron star instead, held up by quantum pressure. This limit isn't perfectly sharp because it depends on the star's composition, rotation rate, and magnetic fields. But roughly 3 solar masses divides neutron stars from black holes in nature. No stable object exists between them, according to our current understanding. This mass gap is interesting because it means stellar collapse produces either neutron stars or black holes, nothing intermediate or in between. However, primordial black holes from the early universe could theoretically have any mass, including very small ones down to microscopic sizes. And intermediate mass black holes might form through other processes like multiple mergers in dense star clusters or direct collapse of gas clouds. The 3 solar mass limit applies specifically to stellar collapse, the most common formation mechanism we can observe directly today. Other formation channels might populate different parts of the mass spectrum. Fact 97. Black holes warp spacetime so severely that unusual orbits become possible that cannot exist in weaker gravity. Photons can orbit a black hole at a specific radius called the photon sphere, circling endlessly if aimed perfectly tangentially. These orbits are unstable, meaning any slight perturbation causes the photon to spiral inward or escape outward, but they theoretically exist. Massive particles can have plunging orbits that spiral inward, crossing the horizon, orbits that circle many times before escaping back to infinity, or bound orbits that repeat periodically like planetary orbits, but with stronger relativistic effects. Near the innermost stable circular orbit, particles move at significant fractions of light speed, sometimes 30% or more. Inside this radius, no stable circular orbit exists at all. Particles either fall in or follow complicated spiraling trajectories that don't close. These orbital dynamics are far richer than around normal gravitating bodies like planets or non-relativistic stars. The strong curvature creates possibilities that weaker gravity doesn't allow. Understanding these exotic orbits helps interpret observations of matter near black holes, like the quasi-periodic oscillations seen in X-ray emissions, and tests general relativity predictions in strong field regimes. Fact 98. The cosmic expansion of the universe doesn't affect black holes themselves despite affecting the space between galaxies. While space between galaxy clusters expands, carrying distant galaxies apart at accelerating rates, bound systems like galaxies and black holes don't expand with it. Gravity holds them together against the expansion, keeping their sizes fixed. A black hole's event horizon doesn't grow due to cosmic expansion affecting it. Its size depends only on its mass through Einstein's equations. Similarly, planets don't drift away from their stars, solar systems don't inflate, and galaxies don't expand internally. Only the vast spaces between galaxy clusters expand significantly, where gravity is weak. This shows that cosmic expansion affects only regions where gravity is weak compared to the expansion rate. Where gravity is strong enough to bind matter together into gravitationally bound systems, expansion has negligible effect. Black holes, being the strongest gravitational systems possible, are completely immune to expansion effects. They remain stable regardless of what the surrounding universe does, unaffected by dark energy or the Hubble flow. Their event horizons remain constant in size unless they accrete mass or merge. Fact 99. Black holes have inspired philosophy as much as physics, raising questions that transcend pure science. They raise profound questions about existence, reality, and the nature of knowledge itself. What does it mean for something to exist if we can never observe it directly, if it's forever hidden behind a horizon? Can information truly be destroyed? Or must it persist somehow in the universe? Does the interior of a black hole exist in the same sense that observable regions do, or is existence itself observer-dependent? These questions blur the line between physics and philosophy, forcing us to examine foundational concepts. They force us to examine what we mean by concepts like existence, causality, and information at the deepest levels. Black holes challenge not just our equations, but our intuitions about reality and how it works. They show that the universe contains regions fundamentally disconnected from our experience, places where we cannot go and from which no information returns. This has implications for epistemology, the philosophical study of knowledge and its limits. Some things might be unknowable not through practical limitations of technology or human lifespan, but through fundamental physical principles built into nature. Black holes force us to accept limits to knowledge itself. Fact 100. Despite decades of intensive study by thousands of scientists, black holes retain their mystery and continue surprising us with unexpected discoveries. Each new observation brings findings that don't quite match expectations or predictions. Black holes in unexpected mass ranges that models didn't predict, spins higher or lower than theories suggested, merger rates different from what simulations indicated. The first black hole image revealed features and asymmetries that some theorists hadn't anticipated. Gravitational wave detections found systems that formation theories initially didn't predict, requiring modifications to models. This ongoing capacity for surprise shows that we still don't fully understand these objects despite great progress. They're more varied and complex in their actual behavior than early simplified models suggested. Future observations will undoubtedly bring more surprises and puzzles to solve. Perhaps we'll discover entirely new types of black holes or phenomena we haven't imagined yet. Perhaps primordial black holes will be confirmed, or we'll detect Hawking radiation, or observe black holes in unprecedented detail with next-generation telescopes. The mystery remains alive and vibrant. Black holes continue to challenge, inspire, and teach us about the universe and ourselves. They stand as reminders that the universe contains wonders beyond our current understanding, waiting to be discovered by future generations of scientists, astronomers, and curious minds looking up at the night sky.